Swayam Prabha. Digital India. Educated India.
Hello and Namaste. Welcome back to the course on Geographic Information System. So, in the last week, we have learnt about data models. What are different kinds of data models? How do we handle data? And now, the third week, we looked at how the data is generated, right? So, the next week, we have looked at how the data, once the data is generated, how do we handle it in terms of data model. Now, whatever the data that has been generated, so you need to understand the data quality. So, to understand this data quality in this week specifically, we would look at what are the different data measures, data quality, data assessment techniques, errors that may have. So, these are actually the overall errors where most of us would have it, but I am not going into some very detailed specific details wherein which actually says that this may be an error, but I am giving you an entire list of errors and quality checks that the entire database or the entire population who may be handling GIS may have. Okay, so this is not very specific, this is for the entire population, but only thing is that if you can understand that what are the necessities, what may be the errors, then it would be really good enough for you to understand how the errors may come and how do you mitigate it. Okay, so in today's class, let's look at data quality, error and uncertainty in data in GIS. There are certain uncertainties associated with GIS, how the data is stored, how the data is manipulated. So, we will look at it. And then measures of spatial data quality and key factors. So, we have to also look at how do we measure a data quality. So, if there are certain data measures or the factors that are governing this quality, then we have to look at those. Then accuracy and precision. This becomes extremely important when you are actually putting out this in a public domain. If you do not say how much accurate is your data, and it may not be the users may not be able to adopt it for the real scenario when they are trying to look at your model. But if you have to be precise, you have to be accurate. So, how much accurate are you? Not all the data, as I said in my previous classes, can replicate 100% of the real world, but if it can replicate a certain percentage of the real world, then it is assumed to be accurate to that extent. So, what are those measures? We will look at it. What are the precision factors also we will look in this particular slides. Then we look at what is positional accuracy and attribute accuracy. Both of these are extremely important in terms of when you are looking at the database. Then finally, completeness and logical consistency. Is your database or GIS data that you have already put in the database complete, or has certain consistency, has some logic in it? If the logic is missing and the logical consistency is missing, then your database may not provide us the best results. So, how do we look at it? We will also go through in this particular set of lectures. Now, first, when we look at data quality, the first thing when you always see the term quality, so one thing is that when you go and buy grocery, so you try to look at the quality maybe in terms of price, maybe in terms of certain brands, maybe in terms of certain size of that particular product, or size and shape or the color of that particular product when you are normally buying in a grocery store. But in GIS, it is extremely difficult in terms of understanding data quality. Okay, so the data quality is more contextual in terms of having a data. Now, when you are looking at manufactured products, as I said, geospatial data do not have any physical characteristics like your color, shape, or maybe your brand. So, there is no physical characteristic that allow the quality to be easily assessed. Only thing that you have is the metadata. Okay, so metadata gives you the data about the entire data. So when you are looking at this quality, so how do we actually look at a data quality? Should we look at in terms of just a measure, or are we looking at in the terms of its different data sources, data measures? That is what we mean by quality here. We nowhere there is a comprehensive list of the things that has to be satisfied in order to have a good data quality. Okay, as far as GIS is concerned, quality is thus a function of an intangible property such as completeness and consistency. So how complete is your data? How consistent is your data? If someone has generated the same, for example, a government agency generates the same data for the next year, what you have generated this year. So when you look at it, because the government agency may have done the entire field, they may have the entire field knowledge and have done the entire field work, and in this year, so they would have got a certain amount of data that is completely true on ground. So the same quality of data that you have published, if there is a consistency, for example, where there is no change, if the consistent is there, and where there is change, if that is again consistent, then it means to say that your data is actually good. So similarly, it depends on what is completeness, what is consistency. So we look at what are different measures of completeness and consistency also. Now the thing that always that creeps into our mind when you are looking at any data is error. Okay, error and uncertainty. So always any data, whatever, irrespective of whatever the tool, software, etc. you are using, has certain error, has certain uncertainty. So that is one of the very major problems that is currently existing within GIS, and is a characteristic of accuracy of a digital geospatial data. So that is why we will say this data is so much percent accurate. It cannot, never a GIS data can mimic a real world. It cannot be 100% accurate, it cannot be 100% true, it cannot really mimic a real world, because real world is a continuous phenomena, and you can see they have their own representations, okay, discrete representations. But when we are looking at here, we put it into real data in terms of converting it from a discrete continuous phenomena to only a discrete phenomena, as maybe line, polygon, etc. So hence it is not easy to mimic a real world, but it is also that you cannot say you have 100% accurate data, because it absolutely does not represent a real world. Then error propagation in GIS is mainly due to process of integration of several data sets. Okay, for example, let us say I may have shown you one of the data sets where I have urban data, I have a drainage data, I have a population data, I have a CDP data, I am in encroachment data, all of these data that have been together. So these are from different sources. If it is a single user who is following a single way of representation of these different layers, then whatever the data that has been collected may be significantly in a standardized form that he is following. But let us say that there are different users who are generating this data, and one user is making use of all these different sources in order to propagate the entire model and build his model. So in that case, there may be several errors, okay, errors or different standardization techniques that people have used in order, so that becomes a very important aspect of a digital GIS. Okay, so to control that, we use certain measures so that the error is not propagated to the entire data set. So the ease with the geospatial data in the GIS can be used at a multi-scale signifies the importance of data quality information. So whatever the data that you have in this particular database, and you can integrate it any number of databases, and also you can use in a multi-scale information and with the same data. So if you are trying to do that, then your the information should be accurate to a very large extent. Okay. Now, what may be the possible errors in GIS? So there are a huge number of possible errors that GIS user can have, but I have listed a few of them which are major errors. Okay. So I have not gone into every detail of this maybe error. If you have polygon like this or polygon closing, so I have not gone into all those details, but I am signifying what may be the major errors which lead to your error propagation in the entire model. Okay. So now when you are looking at errors in GIS, you may have wrongly assigned the coordinate system. So a person has generated one GIS layer, another person has generated another GIS layer. So both of them have a different coordinate system. As I previously said in my previous class, when I am explaining about the coordinate system, both may not sit overlay on each other or sit above each other. Okay. So in order to do that, if you have to do a top down analysis or bottom up analysis, you need to have provided a good compatible or maybe the same coordinate system so that it is easily comparable. Then mislabeling of areas in a thematic maps. For example, I have generated a thematic map. I have 4 categories, let us say. I would say I have, let's say I will take 3 categories, which is urban, vegetation and water. So 0, first class is urban, second class is vegetation, third class is water. Now one of my colleagues developed another map wherein he or she has first class is vegetation, second is urban and third is water. And there is another colleague who develops another map. So he or she has first class as water, second class as urban, third class as vegetation. Now you have 3 different ways of representation of thematic maps. When you are trying to visualize the entire data set, you may not be able to get the exact information, or the information that you would get is actually inaccurate or wrong. Okay. So if this mislabeling is done, not done, so most of the times most of the error comes through mislabeling. Please look at it and have the same labels for the entire data set that you are actually using. I am not saying that every map should have the same data, but if you are comparing, for example, if I am looking at urbanization process, anything that is concerned to urban growth, so I label it in a certain form in the first map, the same thing goes till the 100th map or nth map. Okay. So if that convention is followed, most of the errors are removed. Now the next one is misplacement of horizontal boundaries, the positional boundaries many a times. So this is most inaccurate way, because many of the times people have different sources of extraction of boundaries. So I have already said you can extract boundaries through Bhuvan, you can extract boundaries through Google Earth, you have to extract boundaries through your Survey of India topo sheets. So people have different ways of extraction of boundaries. So when you are extracting the boundary, you have to be extremely again careful with its metadata. Okay, look at the metadata. If all of the maps are generated with the same detailed boundary description, then it will be fine enough. Then mismatch in spatial and attribute data. This is another very important, wherein the mismatch happens with either a spatial data or the attribute data. Many a times it is spatial data rather than attribute data. Human error and digitizing. So we have discussed about these errors. So when you are digitizing certain polygons, maybe a lake, maybe a tree, maybe a building, so there may be a certain errors that creep in because of your digitization. So that errors may also lead to errors in GIS. So that also tells you that if you give a positional information, that shows what is the error, and it may not show where is the error, but it shows how much accurate is your data. Then the classification error, for example, when you are doing a raster land use land cover classification, okay, when you are using a land use classification, the classification error is a very important point where you are trying to understand how accurate is your data. Okay, whatever the data that you have put it in the public domain has to be extremely accurate. If it has to be accurate, then your classification should be very good. In order that this classification is very good, the error has to be minimal, which means the accuracy of the land use that you have generated should be validated in a proper way, and more importantly, that signatures that you have used must represent the entire heterogeneous classes. So we'll look at all of this. We'll look at at least some of these when we are looking at it in the practical class. Then human bias. So there are certain biases. For example, if I'm from let's say from a particular city, so my bias is towards something. Or if I'm looking at only urban phenomena and not the water phenomena, so my bias is towards the urban phenomena. So the more detailed information is towards urban phenomena, whereas the water is neglected. So that kind of bias creep in, which is actually a major source of error. So all of these put forth forms an error. So in order to avoid or inform the user that how good is your data, not any of the data on the earth is 100% accurate. So we have to inform the user what is the accuracy of your map. Okay, so when you are looking at any of the measures, say if someone asks me, okay, you have so many errors, so how do you measure an accuracy of your spatial data? Since you said it is a subjective term, there are various measures of looking at spatial data accuracy. For example, when I say data accuracy, it may be a positional accuracy, it may be a attribute data accuracy. When I look at positional accuracy, it is absolute and relative. Okay, then we have data consistency. So data consistency is extremely important. How we'll measure, we'll also look at that. Data completeness is one measure of data quality. Then data timeliness. Okay, so if you are generating a regular data, so the regular intervals of time is extremely important in order to understand what the data set actually combines. Then there may be some more concepts like lineage and accessibility. When I say lineage, it is how the data has progressed from its birth, or from where it has been born, and till the usage, how it has progressed over time, how it has been improved, degraded, etc., over a period of time. So that is what is called lineage. Then you have accessibility. Accessibility is another factor wherein in today's context also, though we have a huge set of data that has been put out, some very important crucial data about maybe land area, maybe about the statistics of a city, etc., many of them are yet in closed domains. Though you can get so many details in Google, look at Google database, Google extract information from the earth surface through virtual globes, etc., but then also you have certain limitations on accessibility of this data, which is which may be extremely accurate. Okay, so such things also, looking at it, we can say what kind of data quality it has. If it is quite accessible, we can compare the data quality and understand how good the quality of the generated map is there. Now, as I said, so when we look at it, we have to look at it in 6 different ways. The first way, as I said, is completeness. When I say completeness, it is degree to which the necessary data is available for use. Okay. Next, uniqueness. So it means that it is a degree to which data is unique and cannot be mistaken to any other entities. Okay. Then you have consistency, degree to which the data is equal within or in between two data sets. So this is what is consistency. Then other one is validity, a degree to which the data is within the defined requirements like format, type, and range. So this is also extremely important. And when you are looking at accuracy, degree to which the data represents the reality. So that is what we are trying to look at them, mimic the real world. So this is what is extremely important in terms of mimicking the real world. And last but not the least, it is timeliness, degree to which the data is available at the time it is needed and the amount of data that is available over a time bound period. So that is also extremely important in terms of data quality. So please remember, these are the six key factors when you are looking at the GIS data, when you are looking at the evolution of data. So look at all of these aspects. So once we have understood what is data accuracy, we will look at what are the aspects that are considered for data accuracy. For example, the first thing that actually starts with when you are measuring a data accuracy is the aspects of data acquisition. So how the data is acquired, what are the needs of acquiring that particular data, why the data has been acquired, okay. Then the costs that is involved in acquiring the data, accessibility, and the time frame. Other than this, the method at which it has been acquired also matters. Though I have not listed here, method is also a very important factor in terms of acquisition of a data. Then when we are looking at quality, as I informed you before, quality can be defined as one or more characteristics of a geospatial data that describe the extent to which it is for use. That's it. Okay. So even if let's say that there is no data available at all, you have a bad quality data, then also that data is good for use. But if you have huge amount of data in the same domain, and if you have a bad quality data and if you have a good quality data, then obviously you will go for in a good quality data in order to see how good that particular data is. So that is, or utilize that data for to extract some information out of it. Now when you are looking at accuracy and measurement of accuracy, so when we define accuracy, so you should be extremely careful. It is the degree of correspondence between data and the real world. What I mean to say is the data model and the real world model, fundamentally controlled by, so here I am very specific, it is fundamentally controlled, please be careful here, fundamentally controlled by the quality of input. If your quality of input is wrong or bad, then your entire accuracy is bad. Okay. So many of people, when they are doing the land use classification, they come back to us and say, sir, we could not achieve a good accuracy of land use classification. Exactly, because the amount of field investigation that is involved, even looking at visually the scenarios that is in the real world and trying to propagate into the data model, or looking at the real world data, collecting the data, so all of these would be missing. So that is where the quality of input, when I say quality of input, you have to have certain field measurements in order to see that your data set, whatever you have collected, doesn't have any bias. So once you have collected certain data from the ground and have put into the database, along with that you have certain data that you input based on your perception, based on various degree of perceptions. So all of these put together will give you a better accurate data rather than using just a biased data. So always remember that it is your input that actually matters when you are looking at the quality. Then when you are looking at the measurement of accuracy, so there is standard deviation is considered to be the measure of accuracy. Basically, the first thing that you do is that you populate the entire database. Then once you have populated it, you look at what is the mean of for example, if you are looking at the land use classification, look at the mean, then you look at the standard deviation of that particular data. So you know what are the different outliers in that particular data set, which can be either removed or which can be maintained in such a way that it provides some critical inputs during your classification. Most of the time these outliers are removed. Okay. So so that's about accuracy and measurement. So the next thing that we would look at is the error ellipsoid. So this is another basic thing that people consider to be a mistake. So how does it actually happen? For example, when you are surveying, error ellipse and error ellipsoid are utilized to visualize the uncertainty points. When I say error ellipse, it is a two-dimensional image. When I say ellipsoid, the ellipse rotated about its central axis, okay, or the primary axis. So this is nothing but a three-dimensional figure. So when you are looking at error ellipse, so for example, when you look at this here, so this particular thing here is nothing but your minor axis. Whatever you see here is a minor axis. When you look at this, this is a minor axis and this is your major axis. Okay. So this is your ellipse that we have considered. Okay. Now with this, if this is the ellipse that we have considered, Now let's draw a box that is actually connecting the 4 different points that are one is the farther away and the other one is the closer. So 4 different points as 2 pairs. Okay. So once you have done this, the probability of any of the point that is lying outside the standard ellipse is much larger. Okay. If these ellipsoids are used for better results. So when you are looking at the probability of that particular point, if the probability of point here, then that particular point is in a correct shape, whereas if it's a probability of a particular point outside this particular ellipsoid, then you probably have to look at what kind of data sources you have considered. Okay. So when you are looking at this particular observation, the likelihood of observation or measurements lying within the given boundary is actually known as confidence. Higher the number of confidence, which is expressed in percentage, higher the amount of confidence, better is your data. Lesser the amount of confidence, less is your data. If you have huge number of data points that is lying inside this particular area, then you have your data is accurate enough to consider for the analysis. If there are some data points which are outside, these are those erroneous pixels which may not be actually considered erroneous data points. So looking at what is the amount of proportion, that gives you exactly what is the error ellipsoid. So that is why we draw an error ellipsoid and look at what is the proportion of points that is getting into this ellipsoid and what is the proportion of points that is not in the error ellipsoid. So this is how you measure your error as an factor. Next, when another thing is the random and the systematic error. Deviations are normally it is random, but many a times it is systematic. Okay, but 90% of the time it is random. So these random errors can be corrected through various measures. I would not go into details of these measures because these are this has to be looked at when you have the entire data set. But when you are looking at the systematic data are computed using various measures. For example, using this particular equation. Okay, so that gives you the how the systematic error has been propagated through the same source. It may be originating most of the systematic error originate from the same source, keep that in mind. Okay, so that is how you look at the random error and systematic error. But when you are looking at systematic error, see, it is the serious error that occur in the data. It may be due to malfunction of a particular sensor, it may be because of the error in the type of sampling that you are trying to do. So these are the errors that have to be always removed. So if these errors are not removed, then you are probably having the data set, your data may have certain issues when you are processing the entire data. So which means to say that you may give wrong outputs or wrong decisions when you are actually trying to understand the top down approach or the bottom up approach if you have certain issues like this. Redundancy of observation is used to remove this blunder. So redundant observations, many a number of observations can be used to remove this blunder. Outliers, which are probable issues, are to be removed by statistical testing. Errors may also appear in the data processing part. So that kind of errors is it is user specific. It cannot be looked at in terms of a theoretical aspect, but data processing errors also may creep in when you are looking at the systematic error point of view. Next is the precision. It is exactness of the measurement of a description. For example, I have different circles that I have put in here. When you are trying to actually provide a point that is actually fitting the first particular circle, the central circle, then it is accurate and precise. If the same point sits somewhere else, it is inaccurate. For example, in all of these three data sets, for example, when you see in the second case, this is neither accurate nor precise. But when you look at it in the third case, this particular thing is accurate enough. It is closer to whatever is the particular model, but it is not precise. Okay, it has certain amount of accuracy. It may be 80, 70, 60% accurate, but it is not precise. but the first figure is precise. Then the last one is neither accurate nor precise. Okay, so you have to look at what kind of data that you are actually handling and how this data is either accurate or precise. So it also expresses the repeatability of measurements, the size of the smallest feature which can be displayed, recognized or described. That is very important when you are looking at precision. It can apply to space time, for example daily versus annual, or attribute for raster data. It is the size of also a pixel, for example resolution. Okay, so we have to look at these aspects when you are looking. So whether it is accurate and precise, whether it is accurate but not precise, whether it is precise accurate not accurate, or both it is not accurate and not precise. So look at all of these possibilities when you are testing your GIS data. The last two things that we have to look at when you are looking at accuracy is positional accuracy. When you are looking at positional accuracy, it is nothing but a computed quantitative accuracy. Okay, so it is defined as a closeness of locational information to true position. So when you are looking at this positional accuracy, there are two types. One is spatial, other one is temporal. When I say spatial, it is it again is divided into two types. One is horizontal accuracy and the one is the vertical accuracy. When you look at the horizontal accuracy, it is the distance from the true location that is displaced horizontally, whereas vertically it is the distance from the true height and the displace and the amount of displacement that it has in the true height. Okay, so difference from the true height and the displacement that it has from the true height, that is nothing but its vertical accuracy. So we look at both, one in the 2D model, other one is a 3D model. And when you are looking at temporal, it is a difference from the actual time or date. Okay, actual time of your sample collection may be today at 10 a.m. but your data that has been delivered by the Landsat may be at 10:30 p.m. okay, or 10:30 a.m. where the sampling time. So the half an hour difference is your positional accuracy of that particular point. So there may be certain things that are dynamic would have changed over 30 minutes. So when you are looking at your data, you should think about that kind of change that may have happened over a period of time. Then the next thing is attribute accuracy. Attribute accuracy or consistency is the validity concept in experimental design. How valid is your the concept in your experimental design. Then defined as closeness of attribute values to their true values. Okay, how close is the attribute value to its true value? That is a feature in what the GIS maps is supposed to be. Or for example, in this particular line, a railway line is a railway line itself and not a road. So that is what is, so you cannot assign a railway line as attribute value to be as a road, then it's a mistake. Okay, so if that kind of accuracy are verified, then such attribute accuracy may not pose a great challenge in terms of, if you have a good knowledge about the entire space and entire real world, then attribute accuracy may not be a big challenge. But in terms, if it's huge database having huge amount of data, then attribute accuracy poses a great challenge because it has to be populated in a proper way. As I said, the last part of it is whether the database is complete. It is the reliability concept for an experimental design. For example, are all the instances of a feature, be very careful here, are all the instances of a feature when it may be a point line or a polygon in a GIS or a map, a raster value in a map claims to include in fact that is there. Okay, so that is what is completeness, whether that is in the real world model. So if everything is correct, then your data is kind of complete. Then partially a function of criteria for including features, that is when does a road become a highway. Okay, what kind of I mean, if you have some information about that, then it becomes an information that is actually complete. Then whatever said and done, if you want to measure completeness, look at the data that is missing. If you can satisfy that criteria of what data is missing, then your most of your database or the data model is complete. Then the completeness also refers to and the absence of features. Features, when I say features, these are the data model, events in the data model or entities in the data model, okay, their attribute information, whatever the attributes that are stored, their relationships with the spatial data, what are the relationship that has been built. If there are certain relationships that are cross cutting and are not there, then you have to build upon that. In comparing data that is defined in the entire data model, then if you have understood the entire space, that is the spatial aspect, then the database along with the data and its relationship, or the entity and its relationship, then your data is complete. If the entire thing is not validated and it's not correct to the real world, then you have incomplete data. When you have incomplete data, it means that your database is most inaccurate. Okay, so please look at this aspect. So this is where most of them have a issue when they are developing a entire model. So they are not looking at the entire boundary first, what is the aspects that you consider in your model and what is the aspects that are not. They have entire set of aspects that they consider, and finally they would not be able to find out certain entities that or the information about certain entities at certain places which may be needed for to complete the entire database. So look at the completeness of the database. The final thing is logical consistency. So the presence of a contradictory relationship in the database, the topological consistency that is there in the entire data, and the correctness of explicitly encoded topological characteristics of a data set. So this is extremely important when you are building the data set. So when you are looking at the topological data set, please see that how consistent this topological data set. You cannot have a topological data set with a sudden uneven way of representation. So please look at if there are certain things like that, correct it, edit the entire data, edit the data and correct such issues. So when you are looking at this, there is non-spatial and spatial. When you are looking at non-spatial, for example, just to give you an example, some crimes that are recorded at a place of occurrence and others where report is taken. Okay, so sometimes the crime happens and immediately it is recorded by the police, or some of the crimes that are reported in the police station. So these are non-spatial entities. Okay, but it should have a logical consistency. Data for one country is for 2000 and the data for the other country is for 2001. So which again doesn't have a logical meaning in terms of consistency. So you cannot compare both of these. Both the countries should be the data should be comparable for 2000 or 2001, whichever you have. Then annual data series not taken on the same day or month, that's also extremely, I said the time, the month, the minute is extremely important when you are actually comparing two data set, especially if you have remote sensing data. The time, the day, etc. plays a very important role in terms of what kind of data you have and how you are analyzing the data or comparing the data. Then data uses from the different sources or estimation techniques for different years. So lineage is very important aspect. Then look at how this data has evolved also is important. And when you look at spatial characteristics, overshoots that we have seen, there are a lot of errors that when we are actually digitizing, okay, overshoots, gaps, all these are different errors. So look at those errors that may have creeped into the data. So correct those errors so to have a logical consistency. Otherwise, if you are trying to find out the area of a polygon in the entire data set that you have already generated, you may not be able to find out this certain polygons which have these errors, whether it is overshoot or undershoot or having gaps. So that will give you a lot of errors when you are trying to calculate the area. So these are certain data quality checks, the errors that you may encounter in a larger issue when you are actually looking at. But when you start using the GIS data and start populating your database, I am sure you will find out huge number of errors that may creep in. So for every error there is an I mean troubleshooting that you need to do, and maintain the entire database in a proper way. Okay, so if there are huge number of sources, get to the common platform, see that your data is interoperable, and use it in the way that it has to be applied with. So keep this in mind, look at the standards, look at what are the different ways of handling the data, and then use that particular data. Otherwise you are going to mess with the entire data set. To summarize this particular class, we looked at what is the data quality. Okay, what do we mean by data quality? We understood that data quality is not a measurement for a GIS in terms of physical aspect, but it is a measurement in terms of how the data is represented. Then we looked at errors and uncertainties in the data. There are certain errors, there are certain uncertainties, the way we look at. We also look at how do we capture these errors in my probably next lectures. And then accuracy and precision. So not all data should be both accurate and precise, or it not all data will be both not accurate not precise, but it may be accurate but not precise, it may be precise but not accurate. So all of these things are possible. Then you have positional and attribute accuracy. What is the positional accuracy? How the positional accuracy is extremely important and how it is quantitative. Okay, whereas attribute accuracy is the quality of the attributes that you have, where you have not either have not connected it with relationships, or entities are not represented properly. So all of these are very important in terms of looking at data and data quality. And very important thing is that it is complete and consistent. So if the data is complete and consistent, then this data has certain value when you are applying it to the real world. So probably in the next session we would look at the measurement of positional accuracy, the sources of errors, and how do we overcome these errors in next 2-3 lectures that I would handle after this class. Till then, let's meet in the next class. Thank you very much. Have a nice day.